example. So in particular, we were supposed to do tutorials 3 to 5, I believe. Yes, 3 to 5. However, I noticed that we are already a very advanced group, and we have really already done these tutorials yesterday within the different things we did, the GUI and so on. The tutorial 3 was really just adding a new section. So we had initially just the soma, and tutorial 3 is showing you how to add a new section, the dendrite, which I think we kind of did more or less, but in any case, it's relatively straightforward. So you can just have a look here, and it's just adding the same structure that we had before, with the exception of the topology that you have to add, and that is an extra line to connect the dendrite to the soma. And the other one was using a simplified cell model, the Sikevich cell. However, this example, the implementation of the Sikevich cell is a bit weird because it uses a section and then adds the Sikevich as a point process inside the section. So it's kind of an ad hoc solution. And we are actually moving towards a different implementation. So I didn't think it was very useful to teach this one right now. And then tutorial 5 is this position and distance-based connectivity, which we actually did already via the GUI. So this is tutorial 3, the one that we saw that also had the reaction diffusion. It also included some of the stuff connecting, let me see the connectivity rules. Yeah, this thing here, for example, where we had the connectivity depending on the postsynaptic cell cortical depth. So we already saw this. We saw the delays that are based on distance, the distance between the two cells divided by this propagation velocity. And we saw this other example where the probability dependent on the probability of connection decayed exponentially with the distance between cells. And give me 1 second, I'm gonna stop the dishwasher. This is making me crazy.
So if I've got a morphologically realistic model and I want to connect to dendrites, but I only want to connect to dendrites sections that are such and such distance away, so I want a distance-based rule, but for a compartment, is there a way to implement that?
So you want to connect on
to dendrite sections so far away.
So far away from the soma or in absolute coordinates in the circuit?
So if I have two morphologically realistic cells, I want one cell connected to the other, but only dendrites 200 micrometers from the soma of the second cell.
Okay, so we have something, another structure that is called NetParams subconparams, like subcellular connectivity parameters. And there you can define this kind of more complex dendritic distribution rules. In particular, you have one that is a sort of a 1D or 2D probability distribution that maps over the cell morphology. And you can say, for example, here at the top in the apical tuft, there is a higher probability of connection, and here there is low. And so you could use that to sort of map your morphology and say that only those that are 200 micrometers away from the soma should have connections. But we also are, and this is work in progress, and it's part of the grant, allowing this kind of rules that you just mentioned, so distances from soma, for example, or only those that are within 100 micrometers away from the soma, or those that are further away of 200 micrometers, and it can be like in absolute paths, so tracing the whole dendrite, or in sort of relative distance. So all these kind of rules, they're work in progress, the second set, but with the ones that are implemented already, you can kind of do them already. I can show you, we don't have this plan because it was a bit advanced for the course, but I can show you in the second week how to use what we have, the features we have.
Would you mind typing the name of the command you just told me in the chat so I can look it up?
Yes. Yes. I don't think we have too much documentation on it either, but I can point you to. So to distribute, I'll put it on Slack as tutors. Sign access and then use netparams.subconparams. We have a couple of examples in the examples folder in GitHub, and I'll point you to those after this session.
Thank you.
Okay, so since we had already done the tutorials, what I wanted to do today is show you how to create artificial neurons and how to use these artificial neurons or artificial spike generators to stimulate your network. And this is something that comes up very common when you start building models. You will need, apart from your populations that compose the network model, you will need to provide it with external inputs. And sometimes the easiest way is to create this kind of artificial neurons or artificial spike generators and connect them to your populations. The other way is using what we've done these days, which is the stim source params and stim target params, which also allows you to do something similar. But here, the example we will do today, you will see that it's implemented in a slightly different way. So let me go to the actual tutorial, and hopefully you already have made a copy of this tutorial. It's called NetPyNE Artificial Stim. Okay, so the weird thing is that it needs one of these mod files, because one of the artificial cells that's called a BEC-stim requires a mod file that is called BEC-event.mod. And so we hadn't really tried before how to copy these mod files into the Google Colab, how to compile them, and whether it worked properly or not. And it turns out it doesn't work that well, but we have kind of a workaround that seems to work. So for this particular collab to work, every time you run it, you have to do restart and run all. Otherwise, it crashes for some unknown weird reason we are investigating. But if you do it this way, it actually works. And the other weird thing is that the figures don't show up, even if you use this import matplotlib and the matplotlib inline. So the workaround we found is to save the figure. So at the end here, we're using this. So we're using this save fig option. So this creates a PNG file. And if you go to the little folder here in the left, you will see the file that is generated. And if you click on it twice, you actually see it on the left-hand side, right-hand side. So you can actually, run the simulations using the weird restart and run all, and then open the figure and see it here. Very easy. So let's look at what we have here. Okay, so we are doing similar things as yesterday. We're just importing all the NetPyNE modules and packages, and then creating the two objects that we need, as we saw yesterday, the network parameters, netparams, and the simulation configuration. Then for the network parameters, we start by creating the different cell types, as we did yesterday. And the first one we do is a regular Hodgkin and Huxley one compartment cell. The weird thing about this one is that it's implemented in yet another way that NetPyNE supports. And this is like a format which is closer to when you're using objects. So you have this dot notation. And this is allowed because we created like a special modified type of dictionary that allows this type of notation. So you can access the components hierarchically, one inside the other, without having to use dictionaries, which would be something like this, and sometimes it's a bit more cumbersome. And so we said, okay, let's see if we can just use the dot notation, which is a bit simpler, and we created this special type of dictionary. It has its pros and cons, and we don't really use it much, but I thought it would be useful for you to see. And we will see a bit more about this in the session this afternoon on the internal data structures and how NetPyNE is organized internally. But just so you know what this means. So we create this cell. It has very basic morphology and the Hodgkin-Huxley channel. And then it's when the new stuff starts, and we're creating 4 types of new cells. Okay. So the first 2 are these integrate and fire cells. So these are usually the classical computational neuroscience cells that you start with. They're very simple. If you go to the neuron documentation, neuron in fire 2. Here. So they are described here. I will post the here on Slack as well. And they have just a few parameters that you can customize, and you can measure inside some of the state variables. And they are very fast. They're leak, integrate, and fires, and they are point neurons, so they don't really have a morphology. Okay, so we don't really use them much, but I thought it was useful for you to know that you might want to use them for some specific, maybe for some of the inputs around your main model. You want to use simpler cell models that run very fast, like these ones, and you don't really need more complexity. Okay. And then the second one we have is this guy, which is a similar thing. It's called the integrate and fire 4. It's slightly more complex than the infire 2. It's right here. It has a bunch more parameters, time constants, and so on. So you can read more about this if you want. They're implemented as mod files, and these mod files are part of neurons. So they are built into neuron. You don't really have to add any extra mod files here. So, okay, so we have those 2, and then we have these 2 that might sound more familiar, and these are the NetStim and the VexStim. So the NetStim, at least, we did use yesterday as one of the stimulators. So if you remember, we created, for example, let me see here in tutorial 5, the one with tutorial 3 in the GUI, we had this thing here, stimulation parameters, stimulation source, where am I? Here. The source stimulation parameters was a background thing of type NetStim. Okay. So this can be a bit confusing at the beginning because it seems you can use the NetStim in 2 different ways, and that is correct. So you can use them as a source of stimulation and then connect to all the cells, or you can create a population of cells of the type NetStim. Okay, in the same way you can create a population of cells of the type infire, integrate, and fire 1. The NetStim is also a type of artificial cell, a very simple artificial cell that generates spikes at a specific rate that you set, and as far as I know, cannot receive inputs. So it's very simple, but in a way, it's also an artificial cell. So what we're doing here is just creating a population. Well, down here, we're going to create a population, but first we have to create the cell type, which in this case is going to be NetStim. Note that when we define cell types that have morphology, the arguments of this dictionary include something called sex, because you have all the list of sections, the soma with the channels, and so on. For when you create cell types that are artificial point neurons, the only thing you need to add is this argument called cell model, which tells you basically the name of the artificial cell or the mod file that you're going to use. In this case, NetStim 4, this one infire 4, infire 2. And then you can add a number of parameters. For example, for the infire 2, I just added this one here, IB, which I don't even know what it means. And here I added this tau parameter. So you can set the parameters of the point neurons here when you create the cell types. So for example, if I wanted to add something else, tau m for the infrared 2, I could add it directly here. So, tau m. I'm gonna remove it because I don't know what it does. Okay, I think I had a question here. Yes. What are the two different uses of nestings? Again, yes. So the main difference is that when you create it as a stimulation source and use the stimulation source and stimulation target, what happens here is that the netstim, you're essentially creating a separate netstim for each of the cells that you connect to. So imagine you connect this netstim to 100 cells, because this cell type E and I in total form 100 cells. What NetPyNE does behind the scenes is create a separate netstim object, each with its own randomization and different spike times, and connects each of those to each cell. So if you have 100 cells, you're going to get 100 netstim with this method. Okay. If instead you create a population like we're doing here, you create a single population of 50 netstims, you can then connect that population to a population of cells in whatever way you want. It's not going to be one-to-one, but it could be with a probability of 20% or with a convergence or whatever you decide. So you're either treating these netstims as a one-to-one stimulation to the cells, or you are creating a population of netstims and can connect them to other cells in whatever way you feel. So maybe it's a bit complicated to visualize now, but when you start building the models, you will see the difference and why you might want one or the other.
So, Salvador, if you want
Yes.
to create correlated input activity to a network, this is the way. So, with that, you create here a population, and then with the diversion to the target population, you can create that a single neuron in this stimulation population project to several neurons in the target population. So you have correlation.
Yes.
Yeah. Okay.
Yes, I'm not sure why the correlation is, but I believe you. But yes, if you wanted to have divergence, so a single presynaptic artificial netstim project to multiple cells, you would have to use this method. The other one is going to be a one-to-one mapping. Okay. Any other questions? So right now we have just created 4 cell types of the 4 different artificial cell types. Okay, so the next step now is to create the populations. So first we start by creating a regular population of the pyramidal cell, which is the Hodgkin-Huxley multi-compartment neuron, just one compartment. This is the same as we've done before. And you see here that creating the populations of the artificial cells is exactly the same thing. You follow the same method. So I want to create a population of this integrate and fire cell that I define here. So I just label the population. I say the cell type is artificial integrate and fire 2. And I want 100 cells. Okay, so same analogous structure. I do the same for the infire 2, infire 4. And then I have a couple of special cases here with the netstim and the vextim. So let's see first the netstim. So here what I can do is define some of the properties of this population of netstims directly here in the population. So for example, the rate, things that before I defined in the stim source. So here, this kind of things like the rate and the noise. Okay. When I created the source of stimulation, I can now, when it's a when I'm using a population of net stims, I can define them in the population definition itself. So I can say I want 100 cells of this cell type that fire on average 10 hertz, that have a noise of 0.8, 80%, start at 1 millisecond, and use a seed. So this is the randomization seed that we also mentioned before, of 2. So this allows you to reproduce the simulations and also have variability if you wanted to do that by changing the seed. Any questions about this one? Okay. And then we come to the vexstim, which is one of the most useful, because the vexstim in neuron allows you to provide a list of spikes, spike times. So you provide before the simulation, you send it a list of spike times, and then this happened during the simulation at the specified times. So in NetPyNE, we have used the vexstim to provide the user with a lot of sort of built-in functionalities for providing inputs. And so let's see how this works. So we start first by creating a population of vexstims. We say the cell type is this artificial vexstim that we defined up here, and that we want 100 cells. Then, similar to the NetStim, we can define the average firing rate is 5, noise 0.5, and start at 50 milliseconds. Okay, so you already have some flexibility in terms of when to start and so on. And then one of the things you can do is this special argument here that says pulses. Okay, and what this means is that you're going to create a temporary pulse. So you're going to change the firing rate of those vexstims during a period of time, and it's going to change to some other firing rate. So this allows you to, generate some kind of artificial stimuli where you want to provide pulses at intervals or increase the firing rate at some times and so on, or even decrease. You might have a constant firing rate and you want to decrease it and then go back up. So the syntax is very straightforward. So you specify the start time, 200 milliseconds, the end time, 300, the rate that you want to change it to, and the noise level. So this would be like the base parameters, and then you have pulses that change these base parameters at specific periods of time. The other thing you can do, which I didn't include here, is provide a list of spike times. Let me find the syntax for that exactly. Let's see. Here. So you can say something like this. Let's copy it here. Here. So instead of having a base rate level, firing rate of 5 hertz fixed, I can provide a specific list of spike times. And you can actually combine this with the pulses. So both things would happen. And so the specific list of spike times is just a list in Python that provides the times in milliseconds. You can combine and generate this list however you want. So in this way, you can provide very complex patterns that you can generate outside of NetPyNE. Maybe from recorded data if you want. We've also used it for that. And this list can actually be two-dimensional. So in this case, we have a single dimension list. So all the 50 cells will have the same pattern. But if you wanted, you could do a 2D list. Like this. And so on. And then those represent the spike times for each of the cells in this population. Okay, so if you have 100 cells, you would need a list that has 100 elements inside, each being a list of spike times for each of the cells. Okay, questions about this? I'll see something in the chat. Does the noise parameter mean something if you specify spike times? No, you're correct. we could remove this, and also the start. Yes. So if you use spike times, you don't need those 3 parameters. If you don't use spike times, you need, well, you can define the 3 of them. These 3. Okay, so of course this is a lot of information, and you need to practice and play with it to get a hold of it. But I just wanted to introduce the concept, so when you get to you building your models, you have these resources to provide inputs. Okay, so I'm gonna move forward. Here we have a synapse. We call it AMPA synapse, the same way as we defined it yesterday. And we have created 4 connectivity rules. And these are kind to illustrate the things that you can do connecting these artificial cells and real cells, as well as the stimulators, the net stims, which are also artificial cells. So first one we have is we want to connect the net stims to the pyramidal. So remember, the net stim is just this population of net stims with 100 cells and a firing rate of 10 Hertz. And so we want to connect it to the population of pyramidal cells, single compartment, with a convergence of 3. So each pyramidal cell is going to receive input from 3 net stim cells from the population of net stims, randomly selected. The weight is going to be 0.002, and using the AMPA synapse. Delay is going to be selected uniformly from this range of values between 1 and 5 milliseconds. Questions? Okay, so next connectivity rule is gonna be connecting the BEC-stim, the population of BEC-stims, also to these pyramidal cells. The BEC-stims is also 100 cells with this particular firing pattern that we set. And we're gonna connect them with a probability of 0.4, weight 0.05, and so on. Okay. So this means around 40% of the potential connections that can be created will be created. So if the population of BEC-stims is 100 and the one of cells is 100, that is 10,000 potential connections, 100 times 100. So 40%, so around 4,000 synapses will be created with this rule. And in here, can someone estimate how many synapses will be created with the first connectivity rule?
Would it be 300?
Yes, I heard it in parallel from 2 people. Yes, so 300. So we have a convergence of 3. So 3 connections per postsynaptic cell, and the population of peer is 100, so 300. Okay, very good. And the next one we have is interesting because we're connecting the population of Hodgkin and Huxley single compartment neurons to a population of integrate and fire neurons. So these guys are artificial point neurons. They don't have morphology, but they're going to receive input from these guys who have like a single compartment. The rules, in NetPyNE, it's the same format. Doesn't matter which cell types you're talking about. So you still have the pre and post. The probability in this case is going to be 20%, and the weight and synapse and so on. In this case, I believe you don't really need this synapse because it's not going to be used by the integrate and fire. So we could remove this.
Is there a way to provide inhibition to the integrated fire neurons?
That is a good question, and I believe it might be using.
The weight has to be positive or could be negative?
My intuition was that we might need to provide a negative weight, but I don't really know because I haven't used them much.
In theory, it's possible.
It seems the way it works is the weight, the synaptic current changes by the amount W, by the weight. So yes, so I think if you provided like a negative weight, it should have the effect of being an inhibitory signals. We can try it now. Okay, and lastly, we are connecting two populations of integrate and fire, the infire 2 to the infire 4. And yes, it's the same structure here, probability and weight. So as you see, we are making different types of connections. So from this artificial cell to multi-compartment to multi-compartment to artificial, and artificial to artificial. Just to show that independently of the cell type that you're using, NetPyNE treats them all in the same way. And in the backend, it will implement them in very different ways, but for the user, it's all homogeneous. Okay, we set some very basic simulation configuration, record the voltage summa, we're not really plotting it, and plot the raster plot. I'm just going to go ahead and run. You can try that as well. You need to remember, if you rerun more than once, you need to do the restart and run all. So by the way, this works fine if you run it locally in your machine. It's just that the Colab is having issues with the mod files. So you won't see the output here, or at least I don't see it. So I just have to click on the model output raster. And we can, yes.
If you put the percentage matplotlib inline just after the imports of NetPyNE, it seems to work.
Here?
Yes. No, after importing NetPyNE.
Before the import, okay.
No, sorry, after importing down there. After importing NetPyNE.
Okay. Sorry. Here.
Yes.
Okay.
I put after the both from, and it, yes, it seems to work.
Okay. Yay. Obviously, it has to go there. So I'm gonna save the this Colab in case you wanna clone it, but it's for those who missed it, you have to add this matplotlib in line after the imports here in this cell. Obviously. Okay, so great. So we have the output here now. So anyone want to try and explain what the hell we're seeing here?
So I think the bottom two rows, like the two colors at the bottom, are the input from NetStim and VecStim. So the VecStim, I guess there's both a background underlying rate and pulses. Is that true?
Yeah. Yes.
Okay, so then the more concentrated area of the VecStim would be where the pulses were set. And then you can see that the pulses, because this stimulus was connected to these other populations, so these integrate and fire and pyramidal cells, then they were resulting in pulses of action potentials in those populations as well. Okay, very good. So in particular, so this is the NetStim, which has like a fixed rate of 10 hertz, I think it is. Yes, 10 hertz. The VecStim has a fixed rate of 5, but then has the pulse, so that's what you see here. This is around 10 hertz. The VecStim has a slightly lower 5 hertz here in the background, and then you have the stronger pulses. This is 60 hertz, and this is 30 hertz. So can anyone explain? So the actual connectivity is both of these guys connect to the pyramidal here at the top. Then the pyramidal connect to the infire 2, and the infire 2 to the infire 4. It's sort of from the bottom to the top one, then the top to the yellow, and the yellow to the green. So can anyone explain what we are seeing here at the beginning in this at 200 milliseconds in the pyramidal one?
So Jessica is asking how we get the figures. So you have to add this line matplotlib inline here after the NetPyNE imports. You can also make a copy of the notebook again, so I made the change. Okay, so yeah, can I explain? Anybody explain this activity here in the pyramidal cell?
I think I can explain.
Okay.
I think we are seeing the refractory period between like a in a point they all are spiking, and then they stay quiet for a while, and then other again spiking in 3 lines. And pyramidals are less sensible to this kind of spikes, pulse of spike with higher rate of spike. The different with the integrated and fair model that can spike more than pyramidal cells.
Okay, very good. Yes, so you see that the response of the Hodgkin-Huxley is like it almost gets saturated. It's too much input at the same time from the vexting. So it fires initially in 2 rows, and then due to refractory period or some depolarization blockade, so it cannot continue firing. And we can actually plot the voltage trace to see a bit more about that. Plot traces. Include 0. Oh, crash because I didn't do the restart and run. Okay, yes, so you see here, it's almost some kind of close to this depolarization blockade idea where the spikes get smaller and smaller, and NetPyNE actually doesn't detect them below 0 millivolts. So that's why you don't really see the activity here. Yeah, so that's the idea. And then, yeah, as you mentioned, the integrate and fire have this less realistic behavior, so they follow these inputs in a much stronger, clear way. And you even see the delay between the connectivity from the pyramidal to the integrate and fire. There's a small delay here of the connections, and from the integrate and fire 2 to the integrate and fire 4, there's another small delay here. Okay, so why don't you see spiking activity here in the middle of the integrate and fire 2 and integrate and fire 4?
Is it just subthreshold?
I think so, yeah. So I think there's not that many cells firing here in pyramidal 1, so there's not enough combined input to make them fire. And obviously, if this integrate and fire 2 doesn't fire, then the 4 doesn't fire either. Okay.
I'm sorry, may I ask a question?
Yes, please.
I see that in the vex stim, so in the bottom row, there is also a pattern with initial synchronization and desynchronization over time. So am I right that vex stim is a source of spikes, right? So we actually don't know what's the internal mechanism for their generation.
Well,
so
to start with the synchronization, do you mean this part here between 200 and 300 milliseconds?
Yeah, I mean that you also have a vertical line in the beginning of the pulse and the next one, and then it desynchronizes.
Yes, that usually happens with this noise thing, because if you don't include too much noise, usually the first ones are a bit more synchronized. That's a general effect of how the noise is implemented.
Yeah, okay, so each neuron is like independent and it's just some noise process, right? It doesn't have an internal mechanism for spike generation, neither LIF nor, okay.
We just calculate all the spike times beforehand for each of the neurons based on the properties that the user provides.
Okay, so it's just issues of noise generating algorithm, right? So like artifact of this. Okay, thanks.
Okay, any other questions?
It seems like just looking at it, it seems weird that there's no firing at all of the integrating fire 2 in between that gap, right? Because I don't know how hard they are to make fire, but you'd think that about at least that line of activity in the middle there would do something to at least one of these guys, right?
Yeah, I agree. We can try increasing a bit, see if that makes a change. So this would be peer 2. So maybe try 1.5, see if we got one spike. Everybody's fine. So yeah, so it seems that it's not strong enough, and we're probably just in the randomly chose the threshold there. But okay. So we have any other questions? Okay, so I wanted to do a couple of quick exercises. But I want to finish a bit earlier so we have more time. So let's just do one exercise, which is show that you can use the integrate and fire 2 as a negative, as an inhibitory source. And so change the model in some way that you illustrate that integrate and fire can be used to provide inhibition. I will give a couple of minutes for you to play around with that, and then I'll ask someone for their solution.
Sorry, could you repeat what you just said?
Yes, I'm gonna write it here. So modify the network to show that you can use the int_fire2 population to provide inhibition to another population. And we said that that was probably using the negative weights. But I haven't tried it, so I'm not sure.
Can we also provide another input to population 4? So
you can do it however you want. So it's a free exercise. Just modify it in some way that it illustrates that you can use integrate and fire 2 to provide the inhibition. There are an infinite number of ways to do it.
Actually, I did the same thing, -2, -0.2.
Don't give the answer away. Okay. Okay, so I'm gonna show a quick solution that I did, and then I'll ask for maybe a couple others. So what I did here is first change this input from the pyramidal, the top one, that projected into the infire 2. Now I made it go into both the infire 2 and the infire 4. So I just changed here the target. Yeah, so now it's going from peer 2 to the 2 intergradient amplifiers. And then the one that went from infire 2 to infire 4, I made negative, inhibitory. Okay, so you have this nice effect. So this guy is stimulating both of these, but then the yellow is also inhibiting the green one. So you get like initially, you get some activity in the green from the input of pyramidal one, but then the yellow starts inhibiting it and it stops firing. And the same here. You get initial activity from the input from the blue. So this blue line here starts both of the populations going, and then the yellow ends up inhibiting the green one. So it does work for inhibition. Any other solutions? Hearing noises. Any other solutions?
So what I ended up doing is I connected the NetStim to the first integrated fire models, just to get some noise in there.
Okay, give me a second.
Yeah, I put the weight quite high to like 0.5.
The NetStim, sorry, repeat again, sorry.
I connected the NetStim to the integrated fire 2 population.
So this guy here, you changed the first rule?
I added a new one.
Create a new one, okay. Yes. So I sent to the integrate to the infire 2.
Yep. Okay. Sorry, infire 4. Sorry.
Infire 4, okay. Infire 4 with what values?
Hold on. So weight was 0.5, and the I used convergence 3.
Okay, and yeah, you don't need the AMPA and delay uniform.
Yeah, same thing.
Okay.
And then I inverted the weight from between infire 2 onto infire 4, so minus 0.2. And the idea is that you get noise in there, but then once the infire 2 start firing, you get rid of the noise.
Perfect. Oh. No. Okay, so you have some inputs here from the net stim from the red into the infire 4 into the green. You have some activity, but then when the infire 2 starts firing, it inhibits the activity in infire 4, the green. You have a period here of no activity, and then you start getting some activity again from the input, and again it's inhibited.
Why is it that the inhibition lasts so long?
Yeah, I was thinking about that. I'm not sure. I guess because there is some delay also from getting to here, from the net stim to here. You can see that at the beginning. So I guess that's a bit of the space here, but I'm not sure why it's so big, to be honest.
Can you get traces from the point neurons?
Traces, you mean, like the voltage?
Yeah.
Or something. Yeah, I think you have something that's, let me see. Synaptic current, membrane state variable, CM.
I mean, the question then being whether it's just that, the spikes aren't large enough for us to detect them again.
It's possible. Yeah, part of it is the delays, no? From here to here, from the red to the green, and from the yellow to the green. But we can try to plot it. So it seems to be, I'm going to call it MRTIF. And how did you record this? I forgot. Let me see the NetPyNE recording. I know we had a tutorial on recording. Is Joe here? Okay, I'll check how you record this, and I'll share the code in a bit. It has a slightly different. So I know the var is going to be M, but I think you needed to add something else here. By the way, I think it's a good time to mention this. You can make the recordings conditional. So you might only want to record the b-summa for some populations and this variable for different populations. So you can include here within the dictionary something called cons, in the same way that you do conditions for presynaptic cells or postsynaptic cells, and then say cell type peer. So this b-summa is only going to record it for the pyramidals, and then I would do cons here for this one, cell type infire 4. What's the name of the cell type? This one. But this is probably not going to work because I'm using the wrong syntax to record. Let me just try. Oh, and I'm not including this in the plot traces. So, okay, so another interesting thing here, when you want to plot, for example, from a particular population, you can say here in include, you can put the name of the population, which is pop infire 4. And the index within that population of the cell you want to record, 0. So this is going to record cell 0 from the population infire 4. And we also want to plot for 0, which is the first pyramidal cell. Ah, it worked. Fantastic. So I have no clue what this means. But it's supposed to be some membrane something. Membrane state variable. Oh, maybe that's not the one we want. Current, synaptic current. Yeah. Oh, this is the Infire 4. Yeah, no idea. But something is going on here. Okay, so it seems to be pretty close to 0 when it's spiking, and then it takes a bit to get up here again. Something like that. Okay, so we're gonna
It is
stop
probably
here.
voltage. If it is leaking to great fire, then its variable is basically membrane voltage.
Yes.
And I guess that because the mechanism is not conductance based, but current based, it goes down very much and recovers only after a certain time. So it does not saturate as it would if conductance based.
Makes sense. It takes longer because it's based on the currents. Okay, very good. So we're gonna stop now. We're gonna come back in 10 minutes, and we have a slight change of plans. So first we're gonna do, when we come back at 11:30, a short 20-minute session on, is it plotting LFPs and something else? Tutorial, check. Tutorials. Oh yeah, the stimulation, which we have already kind of done, and then recording and plotting LFPs, which is pretty simple too. And at around 11:50, we're gonna switch and we're gonna see a talk that is happening today from 12 to 1. And this is a talk by Nima Mesgarani, who's a professor at Columbia. He's quite famous because he's done a lot of stuff on reading the brain EEG signals to decode speech. I'll send a couple of papers now. And he's giving a talk comparing the more biological models, realistic models of the brain, to these more modern or more current deep learning models that try also to model the brain activity. And he's sort of comparing both of them. So I thought it was quite useful and relevant to the course here. He's also a good friend here in New York. We drum together. So I just told him, hey, you have 40 new people in the audience. And so I'll send the link to that, and that's gonna start at 12. So, but we should try to get in a bit earlier, like 11:50 or so. So I'll see you guys back here at 11:30, 7 minutes. Thank you so much.
Thank you.
Thank you.